problem of analogy as a topic for our talk. I will try to say something about analogy from the mathematical point of view, from the point of view of the theory of category. I know that this time of the day is not good for mathematics. It's a siesta time, and I shall try to be as pedagogic as possible. I will avoid almost all technicalities and stick rather to some conceptual ideas. The category theory started in 1945 with a paper by Samuel Eilenberg and Saunders MacLean. The paper was entitled General Theory of Natural Equivalences, and one of the authors, MacLean, confessed many years later that the authors had written this paper and they thought that would be perhaps the only one necessary research paper on categories. But today, every textbook on category theory quotes this paper as the one that gave birth to one of the most comprehensive mathematical theories ever. I think that category theory can teach us a lot about the problem of analogy. I practice a lot and it does. This is a quotation of one of the mathematicians, Professor Brown, who argues that category theory is about analogies. But I will skip that and proceed to more concrete material. We are running out of time, so okay. And this is an outline of what I am going to say. First, I will begin with a few words, very few words about the motivation. Then I will introduce the very concept of category and the functor, two fundamental concepts of the category theory. And then I will say something more about two important concepts of the category theory, naturality and adjoint functors. And then I will proceed to a few comments on analogy concept. What about my motivation? Let's start with the philosophy of mathematics. There is an old dispute about philosophers of mathematics. What are the primary mathematical entities? According to one of the schools, very traditional schools, the primary mathematical entities are objects, like numbers. Others claim that there are structures, and objects are but places within the structures. The similar dispute is going on in the philosophy of physics, or in physics itself. According to one school, space and time are collections of objects like points or instances. Here we can quote the Newton's idea of the absolute space and time, which are just sets of objects like points, space or time, a set of instances. Another conception is that space and time are but ordering relations between events, and here the hero of that approach is, of course, Leibniz. These two standpoints in the philosophy of mathematics and in physics are but an echo of discussions which are going on in metaphysics since Aristotle, or even earlier from Presocratics, whether the fundamental bricks of reality are substances or substances like objects, or perhaps a network of relations. And I think that category theory is very important in these discussions. It can show us quite new and unexpected aspects of this dispute. So let us proceed to the definition of category. category is a mathematical structure, in fact a very simple mathematical structure. It consists of the following things. First, objects, and we will denote them by letters A, B, C. Objects can be anything. And then there are morphisms, also called arrows. Let us take a look at the formula, this formula here. We have two objects, A and B, and a morphism between them, or simply arrow. A is called domain of this morphism, and B is called codomain of this morphisms. Morphisms can be composed if we have two morphisms from A to B and from B to C. They can be composed in an obvious way. And this composition satisfies the associative law, which is very well known in, from standard multiplication. It's similar to the standard multiplication associative law. And this is very also important kind of axiom that for each object A, there is a morphism from A to A. So the domain and codomain is A, which is called identity morphism. It changes nothing. And this is all. This is the definition of the category. So in fact, this is something absolutely very simple. And what is astonishing that such a simple thing has revolutionized entire mathematics. So it also contributes a little bit to our discussion about complexity. Very simple thing, and the consequences are enormous. And now let's go back to our motives, to this discussion between objects and structures. So the simple idea would be to replace what is usually called relation with morphism. Of course, relation can serve us as a morphism. The typical example of a category is a set as an object, sets as an object, and functions between sets as morphism. But the point is that morphisms need not be functions, and objects need not be sets. It's much more general. So the idea would be to replace relations with morphisms, which are much more general. However, the term relation is too set theoretic and too laden with philosophical connotations to correctly render the message coming from the category theory. We can say that the traditional relational structuralism, like in philosophy of mathematics, physics, or in ontology, is a bottom-up structuralism in which every relation had to be a relation between some things, some objects. The categorical structuralism, on the other hand, could be called a top-down structuralism. And we have here a quotation from Aude, who is a very well-known mathematician working in category theory. And he says that if we take the perfectly autonomous notion of morphisms in a category, we can build a structure out of such a morphism to our heart's content without even having to ask what might be in them. So we do not need to bother about the nature of objects. So a good idea would be to regard categories themselves as building blocks of the categorical structuralism. So in a sense, to take categories as object in the standard, usual, everyday way of speaking. So let's consider building blocks, categories as building blocks of the categorical structuralism. And then we should look for suitable morphism between categories. And such a morphism between categories is called functor, and is one of the cornerstone concepts of the category theory. And a functor from a category C to a category D transforms objects of the category C into objects of category D, and morphisms of the category C into morphism of a category D, of course, in such a way that the structure of a category is preserved. Of course, it is rather the description than the definition of morphism, but in this talk I avoid definitions. I try to make to only interact with your intuition rather than the strict mathematical reasoning. And then if we treat categories as building blocks of a structure and morphism as sort of arrows between these categories, then we can repeat everything we have said so far about objects and morphism, but on the higher level, so to speak. And now I want to give you some intuitions concerning two very important concepts which we will use to say something about analogy. And I propose to contemplate this little diagram, this little story. Our task in this story is to compare two flights. One flight from the airport source to the airport target with the help of airline F. And another flight from the same source to the same target with another airline G. And we want to decide which airlines offer us better flights. How to do that? Let's suppose that we send two travelers from the source airport, and they start at the same time towards target. One takes the airline F, another one takes airline G. And they arrive to their destination, to the target, and then they meet at the airport and they compare their experiences. So they make a sort of comparison between the results of airline F and the results of airline G. And for instance, they can decide that one of the airlines arrived 1 hour earlier than the other, so it's better. They also can compare other conditions of traveling where the meal was better, etc., etc. Okay, and now let's look at that in a more formal way. This little diagram shows you the same thing. We have a source category, the first airport, and the target category, the second airport, and we have two objects. One object, object A, which is an object of the source category, and we have two morphisms, F and G, these two flights, and our task is to compare this morphism, S, F, and G. So we compare arrows, F and G. And we do that in the following way. We transform object A from the category source to the category target, and as a result of this transformation, we obtain an object FA. Object A, F transformed into the category target. We do the same with the same object A, and we obtain the object GA in the category target, and then we compare. So this dashed line over there, and this is a morphism from the object FA to the object GA already in the T category. So they compare which flight was better, and we consider the family of such morphism TA, and this morphism is indexed by the object A. And now there is a definition. A natural transformation between functors F and G is a family of morphism TA indexed by objects A of the category source, and some other rather obvious conditions must be satisfied, which I omit here, which can be found in my written text on the table. And so we have here the concept of a natural transformation. These two transformations, F and G, are not independent of each other. They have some affinity, and this affinity is called a natural transformation. This is one very important concept we will use in a moment. And now there is another one. We have another story. We have two people, Andrea, which is in the category Rome, and Sofia, which is category Madrid, and they are in love with each other. They want to marry, but they are in different categories, in different cities. They are separated. So how to help them in their desire? Well, there is an obvious way. We should help her to go to Rome with the help of the arrow G, and then we could marry. The equivalent way would be to help him to go to Madrid with the help of an arrow F and be married there. It's very obvious. Of course, we can add some more obstacles and write beautiful romance about that, but this is already another story. And now we do the same now. This is an abstract picture of the same situation. We have two categories, source and target, and two arrows. Arrow 1, arrow F is going from source to target, and G is going to just opposite direction. And then let A be an object of the category source, A for Andrew, and S, Sophia, an object of the category target. And you want to compare object A and S. We want them marry. But they live in different categories. Therefore, we either move S with the help of the functor G to the category source to compare it with A, or equivalently, we move A with the help of the functor F to the category target to compare it with S. And we express this procedure by writing this rather funny-looking formula, which is has somehow historical reasons of doing that. It says that all morphisms from A to GS already in the source category are transformed into all morphisms between FA, A transported with the head of F, S, and compared with S. And then we say, and if this transformation alpha is a natural isomorphism, natural transformation with the concept of naturality defined as previously. So if it is a natural isomorphism, then F is said to be a left adjoint of G, and G is said to be a right adjoint of F. The concept of adjointness was introduced by Daniel Kahn in 1958, and it truly revolutionized category theory. Let's contemplate for a little while the functor G and the functor F, which are supposed to be adjoint functors. The G is almost inverse of the functor F, but it is not quite an inverse. If it is inverse, we would have an identity like in the set theory, but it is not quite an inverse. And there exist adjoint functors between categories that are far away from each other, conceptually far away, so that no connection between them was ever suspected in mathematics. Only after the concept of adjointness has been introduced, many different concepts displayed their affinity, and this contributed to some progress in mathematics. Suppose we have two structures, two categories to be precise, between which there exists a pair of adjoint functors. Then one of these structures gives rise to the other structure, and vice versa. And very often, to establish this relationship without the help of adjoint functors would require long chain of deductions, and sometimes even it would have never been identified. So this concept is both heuristically and also really very, very important. And now we go to our final part, some comments on an analogies. There will be only some comments because I think the topic is very interesting and could be developed much further than I was able to do when preparing this talk. The concept of analogy belongs to the family of those concepts that, being important for scientific and philosophical discourse, are at the same time fuzzy and changing their meaning depending on the context. And in spite of some heroic attempts undertaken mainly by philosophers, linguists, and logicians, we usually use these concepts basing on our intuition rather than on some hard analysis. Just to mention a few attempts to formalize or to define the concept of analogy. Of course, in the classical philosophy in the Middle Ages, there were some attempts to define analogies. In the modern times, some logicians did that. For instance, perhaps the most famous is a little book written by Father Bocheński. The concept of analogy seems to be, from its very nature, multi-faced and adapting its meaning to various situations. So we could say that it is a dynamic concept. This is why the categorical ontology seems to offer more effective means than to deal with this concept with the traditional set ontology. I am using here two expressions, categorical ontology and set ontology. They are, well, described, not to say defined, described in my layout here on the table. Roughly speaking, the set theory presents a certain ontology. Sets are defined, are identified with the help of the function which is identity function. Every set, every element of a set is identical with itself. In category theory, the concept of identity, of course, we can define it the same way, but it turned out it was Grothendieck who noticed that the set theoretical concept of identity is not good for category theory, and he defined identity within a categorical theory with the help of adjoint functors. And it turns out that this newly defined identity is suitable for the category theory, and the identity concept gives, as the name suggests, the identity to a given object or category, and this is why I call it identity, because it identifies, it makes individuum meaningful. So I am speaking about categorical ontology and set theoretical ontology. Our everyday ontology is, of course, set theoretical more or less, because set theory was modeled on our everyday intuitions. But category theory offers much, much richer possibilities. Looking at analogy with the help of categorical tools is so promising that it would require a more profound study, and here I am able to offer only a few short comments which follow. Classically, analogy is defined or described in terms of relations between objects. Categorical concept of morphism, together with its dominance over objects, discloses more shades of the notion of analogy. I say that the morphism is dominating the concept of object. There were also some attempts to eliminate objects from the definition of category. This is so-called objectless category theory, but it is not quite successful because you must use some sort of identity. But nevertheless, we meet here some dominance of morphism over objects. For instance, in many cases, if you consider all morphisms going to a given object and all morphisms outgoing of the given object, you can forget about the object and only work with morphisms. And this can be made mathematically precise. As I say, for instance, the very concept of object is in the categorical setting reveals its dynamical nature. The usual question, what is object, in categories theory is replaced by another question, what is object doing? Remember our little pictures about Andrea and Sophia and the other with the airlines. They are don't saying what is object, they are showing the action, the process. The category concept embraces as its special cases sets, structured sets, relations between relations, abstract and concrete processes, etc., etc. One can deal with this variety of situations not only in the intuitive way, but also in the mathematically precise way. If you want to decide whether two things or situations deserve the name analogous, we must somehow compare them. And the category theory offers many ways of comparison, a great variety of functors with the help of which we can compare objects and also functors between themselves, among themselves. And since there are functors between functorial categories, that is to say, such categories, the object of which are functors, we can also explore analogy between analogies. And it seems that the natural transformation and adjoint functors are especially suitable to this end. Yes, only 2 slides more. A natural transformation compares two functors between two categories. The way of comparing seems complicated, but it effectively detects a certain affinity between them, and it is tempting to call this affinity of functors with the term analogy. And another possibility would be to say that two categories are analogous if there exists between them a pair of adjoint functors. As we know, two adjoint functors between two categories are almost inverse of each other, but they are not quite inverse. So it is another possibility. I would say that it is not important whether we call this and that concept analogous. It is important that we know how to deal with them, and this category theory offers that possibility. So it seems that it's worthwhile to learn how to use categorical models in the service of philosophical investigations. Mathematical tools are much richer than our everyday intuitions and purely verbal distinctions. They are able to reveal unexpected aspects of reality. Thank you.